the solubility of ionic compounds. Now by ionic compounds we know that in ionic compounds one element releases electron to give rise to a cation and another accepts that particular electron to form an anion, and these two ions A positive as well as B negative are held together by strong electrostatic force of attraction. You can say that they are held together by Coulombic force of attraction, and their attraction is so high that ultimately they give rise to the formation of a solid compound. Okay, now this solid compound, whenever is put in water, then immediately the polar water has the capability to give us back the cation as well as the anion, and the substance we said to be, this ionic substance AB is said to be ionized. Now there is a difference in this ionization, that when you put them in water, immediately they are called aquated cation and aquated anion. Suppose you have n number of AB molecules, and if ultimately after dissociation you have n positive ion as well as n negative ion, then we say that the whole AB is completely dissociated, or we can say that whole AB completely goes into the solution, or this particular substance AB is soluble in water. Suppose we have AB, we have given their AB compound, and after some time this AB will not be found here in water, and there is no precipitate, and all the AB which was initially solid has gone to the ionic form, which are not visible to the naked eye, and this particular solution, whatever be its color, will be clear. It will be a clear solution. If it is white, then we will have a white solution or colorless solution, and if the compound AB was a colored compound, if it goes to ionic compound, then we will have a colorful solution, but that will be a clear solution. Now, though all the ionic compounds are supposed to go for ionization at an equal rate, but it has been found that not all the ionic compounds goes completely to the solution phase. Suppose we say that silver chloride, this is a particular ionic compound which is formed by release of one electron from silver, the outermost electron of silver. Silver has the electronic configuration krypton, 4d gain, 5s2. So, sorry, 5s1. Now, when silver releases that particular electron of outermost orbital, it goes to the formation of silver ion, and that electron is accepted by a chlorine to give silver chloride. Now, when they are held together, we have silver and chlorine, and we will be having the ionic compound silver chloride in the solid form. Now, the thing is that when silver chloride is in the solid form, and if we want to put it in water, then it has been found that even if we put it in water, whatever be the apparatus and whatever be the volume of water, and depending on the amount of silver chloride, it has been found that a little amount of sodium chloride settles at the bottom. Okay, or we can see the precipitate of silver chloride residing at the bottom. That means that though this was also an ionic compound, but putting them in water, they didn't go to the solution. In this particular form, we can see that they are either insoluble or they are sparingly soluble. That means a little amount of them goes to solution, but not all the particular thing has gone to the solution. Now, if we bring the rate of degradation or rate of ionization, we can put it in this particular way. Suppose we have sodium chloride and we want them to go to ionization like this, silver ion as well as chloride ion. Suppose I have 10 number of silver chloride, and in the initial state both the silver ion as well as chloride ion concentration will be 0. After some time, this one of the silver chloride molecule gets dissociated, and we will be having one silver ion as well as one chloride ion. That means the forward reaction now starts. The forward reaction means the dissociation of silver chloride or ionization of the silver chloride, or the breaking of the silver chloride molecule has started. So we put this as a rate of forward reaction because the forward reaction is now occurring. After some time this will be 8, this will be 2 and 2. See, mass cannot be destroyed. So if this is 7, this will be 3 and 3. That means the more the number of dissociation, more will be the silver or the chloride ions forming. Now, according to the law of chemical reaction, we know that more the amount of silver chloride, more will be the rate of the reaction, or we can say the rate of the forward reaction is directly proportional to the initial concentration of the reactant. Here it will be silver chloride, or this is the proportionality sign. So if we remove the proportionality sign, we can say rate of forward reaction is equal to 1 proportionality constant Kf as well as the concentration of silver chloride. This we name as 1. But what happens actually when silver goes on dissociating, and as soon as the silver ion concentration as well as chloride ion concentration goes on increasing, silver is a heavy metal. It is quite heavy, having a atomic number 47 silver. So it's a quite heavy element, and instead of existing as ion in water, this is equated silver, no doubt. Instead of existing as ion in solution, silver will have a tendency to combine back with chloride to go back to the solid form, this one. This is because of the heaviness as well as its inert quality or property. So as soon as the silver and chloride ion goes on increasing, as soon as this concentration goes on increasing, the silver develops a tendency to combine with both of them and go back to the initial state. That means the more the number of silver chloride goes in the forward direction to form silver ion as well as chloride ion, and once this concentration increases, immediately there is a tendency for the silver and the chlorine to combine back or bond with one another to give you back the solid silver chloride. So rate of backward reaction will again be proportional to silver ion as well as chloride ion. Now you have the forward reaction also, where one silver chloride molecule breaks down, and you have the backward reaction also, where the silver and the chloride ions will combine with one another to give you back the silver chloride solid. In this state, after some time, you will have a thorough equilibrium between the reverse reaction as well as the forward reaction. You see? And this reverse reaction, if we remove the proportionality sign, this reverse reaction is equal to K backward as well as silver ion and chloride ion. Hence, we can say that after some time, when the rate of forward reaction as well as the rate of backward reaction becomes equal, we have another situation. And the situation is that rate of forward reaction is equal to rate of backward reaction. And what is forward reaction? This is K forward as well as silver chloride, and rate of backward reaction is equal to K backward is equal to silver chloride concentration and chloride concentration. A silver positive, chloride negative. Now the thing is that silver chloride concentration, the amount of silver chloride breaking to give you silver and chlorine, is so small. So there is actually no change in the original silver chloride concentration. So this, if we say that we took one a molecule of silver chloride, almost one will remain, only maybe 0.00001% of it will break down. So virtually we can say that even though we take a number of silver chloride molecule, virtually you can assume that it is almost constant. So that fact is denoted by putting K concentration of AgCl as 1. That means you have taken 1 and it has not undergone any change. And in that case, we will be having the Kb and the production of silver ion as well as chloride ion. So if you rearrange the things, then K forward divided by K backward is equal to silver ion concentration as well as chloride ion concentration, or you can say this both these are Kf and Kb are constants. So you put it as solubility product Ksp is equal to silver ion concentration as well as chloride ion concentration. Now if we take them as positive and negative ion, then we can say Ksp is equal to amount of positive ion produced as well as amount of negative ion produced. Now what are these? These are none other than the ions which has gone into water, or you can say these are aquated ions. So what is solubility product? Solubility product is the product of cation as well as anion which actually goes into the solution. We as a general rule imagine that all the ionic compounds, whatever be the ionic compound, we will get the cation as well as anion. But it has been found that now most of the ionic compounds cannot go to complete dissociation and only fraction of them goes into the solution. Then the product of the actual fraction of the cation as well as actual fraction of the anion will give us the idea about the solubility product. Now what is solubility product then? This is the ratio which gives us an idea whether a particular ionic compound has gone into the solution or not. You see, Ksp is equal to product of cation and the anion. So if the concentration of cation and anion is high, then immediately this means that the solubility product will be high, or we can say the compound is more and more soluble in water. So Ksp, you have concentration of A, it means the cation, and concentration of B, that means the anion. So you can say higher the value of this, anion and cation, higher will be the value of solubility product, and higher the value of solubility product, immediately you will be having more soluble ions. Now sodium chloride has a very high solubility product, and that is why sodium chloride is supposed to be almost 100% ionic. Ionic and 100% soluble. But if you have a salt like barium chloride, this is so heavy. Barium is 56. This is so heavy, though it is a ionic compound to give you barium 2 positive and 2 Cl negative. It hardly goes into solution. Once they break up to give you this, immediately again they combine with one another to give you the undissociated solid barium chloride molecule. So the idea of this solubility product is very, very important, because until and unless we know that this particular compound will be soluble in water or some other thing, we cannot find out actually whether we can apply it in our day-to-day life or not. So solubility product, therefore we can say it is the concentration of Ksp, it is the concentration of the cation, okay, actually which has gone into the solution, as well as it is the concentration of the anion. Now the number of cation and the anion must be same. So we how we put it as concentration of cation is S, concentration of anion will be S. The part soluble cation as well as soluble anion. Why both are similar? Because number of cation will be equal to number of anion, otherwise they cannot balance with one another. Mostly Ksp will be, in this case, will be S squared. So once we have the idea about the S value, we can go for the Ksp value immediately. So many problems are done in, as we say that solubility product Ksp is nothing but the product of the cation as well as the anion that goes into the solution. A numerical mathematical problems are there utilizing this particular principle. Let us study one by one. The first example is calculate the solubility or the amount of solid that actually dissolves. We can say in this way, calculate the solubility. What is solubility? The amount of a particular solid that dissolves or goes into the solution in mole per liter. Now what solid you had given? The solid is silver chloride, and the solubility product of silver chloride is given. That means the product of silver ion and chloride ion, the overall product of silver and ion and chloride ion is 1.8 into 10 to the power minus 10 mole per liter or gram per liter. It is given there. So how you will have to proceed? You can say that we know that silver chloride solid can undergo the equilibrium as silver ion as well as chloride ion in aqueous media. So first of all, we have silver chloride solid. So in the solution phase, initially both the concentration of silver ion and chloride ion will be 0. After some time, as a number of silver chloride molecule will dissociate. So the amount present will be then solid minus S. That means the initial concentration of the solid minus S, and you will be having jiman bhagibo himan hifale gothon hobo. So S is dissociating, you will be having S number of silver ion as well as S number of chloride ion. So solubility product KSP will be equal to concentration of silver ion and concentration of chloride ion. We represent them symbolically as S. Now KSP is given, it is 1.8 into 10 to the power minus 10. So put it here, this will be 1.8 into 10 to the power minus 10, and this is equal to solubility of silver, which is S, solubility of chloride, which is S, that means S square. So S square is equal to 1.8 into 10 to the power minus 10. Therefore, S will be the root over of this particular factor, and the actual solubility will be 1.34 into 10 to the power minus 5. So this is the first problem. Then you go for the second one. Calcium carbonate has a solubility in water. It is given there. Calculate KSP for calcium carbonate, where molecular mass of calcium carbonate is 100. Now you see calcium carbonate, when breaks down, it gives a dye-positive calcium ion as well as dye-negative carbonate ion. So initially we say that the solid calcium carbonate was present and the concentration of calcium ion and carbonate ion were 0. After some time, S amount or S number of calcium carbonate breaks down, resulting in the formation of S number of calcium ion and S number of carbonate. So what will be the solubility product? It is KSP will be concentration of calcium ion and concentration of carbonate. Both these are taken to be S. Okay, so this will be S square. Now the thing is that S is given here and you are asked to find the solubility product KSP. To use KSP, S must be in mole per liter. Now the unit in order to determine solubility product, since solubility product is represented in mole per liter, that is why you have to take S also in mole per liter, or you can take it in gram per liter also. So gram, if you want to take gram or mole, in order to go to the molecular number of mole, you have to have the molecular mass, and that is why it is given at the very beginning. Molecular mass is equal to 100 for calcium carbonate. You can take it as 100. So how to convert the solubility product into a unit having mole? Okay, so how you convert? How many? What is the amount given for solubility of calcium and carbonate? It is 0.018 gram. Okay, it is given in gram. So whatever be the amount in gram, just divide it by the molecular mass, you will get the number of mole. So you are given 0.018 gram per liter. Divide it by molecular mass, which is 100.1 gram per mole. Gram will cancel one another and you will get a ratio. Just simplify this one, you will get 1.798 into 10 to the power minus 4 mole per liter. So exactly, initially you were given gram per liter, but since solubility product is expressed in mole per liter, that is why we have converted this solubility in gram per liter to mole per liter by dividing it into by the molecular mass. So simply now put the mole per liter unit solubility product. So KSP will be S square. Now S in mole per liter is 1.798 into 10 to the power minus 14. So ultimately the solubility product comes out to be 3.82 into 10 to the power minus 8.